I think you can start.
I can
Sandeep,
start, sir? Okay,
please.
sir. I'll go ahead.
Mhm.
So good afternoon, our speaker for this session, Dr. Abhishek Dixit, sir, and all the participants. I heartily welcome you all to this particular session of the FDP. So just let me just give all the participants a brief introduction about our speaker for this session, and then can continue with this lecture. So Dr. Abhishek Dixit received the MTech degree in Optoelectronics and Optical Communication from Indian Institute of Technology, Delhi in 2010, and the PhD degree in Computer Science Engineering from Department of Information Technology, Ghent University, Belgium in 2014. Since 2015, he has been an assistant professor at IIT Delhi, where he has taught courses related to communication engineering and networking. He has also taken up an NPTEL course on principles of digital communications. Before joining IIT Delhi in December 2015, he has served for a semester as an assistant professor at IIT Mandi and as a postdoctoral researcher during December 2014 to June 2015 at Ghent University, Belgium. He is leading research activities at IIT Delhi in the area of optical communications and networking. In this context, he has been involved in the large number of Indian research projects. He has also carried out several consultation projects in the area of railway signaling. He has published over 80 research articles in various international journals and conferences. So with this brief introduction of our speaker for the day, I hand over the session to you, sir. You may please start.
Thank you. Thank you to the organizers for inviting me to give this talk. My talk is, are my slides visible?
Yes, sir. They are visible.
Okay, thank you so much. So the topic of my talk is, the topic of my talk is Li-Fi networks. And in this talk, basically, we will be concentrating on physical layer design of the Li-Fi networks. So this is the outline of the talk. First, we will introduce what is this Li-Fi. Then we will talk about visible light communication system model. I will also introduce what are the differences between Li-Fi and VLC. Then we will talk about multipath channel modeling and characterization. We will then discuss modulation schemes which are used in VLC, multiplexing techniques used, and we will also give some demos of the research activities that have been carried out at IIT Delhi. So let us introduce what is Li-Fi. Li-Fi is a light communication system which transmits data at high speed. So when I'm talking about light communication, it means that I can do communication over visible light, ultraviolet, or infrared spectrum. So visible light you can see in the slide is between 400 terahertz to 800 terahertz. We can use these frequencies, or we can use ultraviolet frequencies, which goes from 800 terahertz to 30 petahertz, or infrared, which lies in this range. So when I'm saying Li-Fi communication system or Li-Fi, it means it's a communication system which can use either infrared or visible light or ultraviolet frequencies for communication. At present, LED lamps use light in visible range, right? So you must have seen in your houses, LED bulbs are installed and all these bulbs emit visible light, okay? And we want to establish communication over these LED lamps because then we can provide illumination coexisting with data transfer. That means we want to provide illumination coexisting with communication. So many people at this moment are using LED bulbs or LED lamps, which transmit light in visible range. So as I have said, Li-Fi means that you can use ultraviolet frequencies for communication. You can go to KAIST University website and you can see several research papers coming out from that group which focuses on this kind of Li-Fi. For visible light, you can look to our research papers. We are using visible light to establish this Li-Fi communication. If you go to ISC Bangalore, they are focusing on infrared light for communication. So these are the examples of the groups which are using different frequencies to enable what is known as Li-Fi. So as we are working primarily on using visible light, so the rest of my talk will be visible light networks or visible light communication networks, which is abbreviated in short as VLC. So what is VLC? It is a short range optical wireless communication technology. It operates in the frequency range 400 terahertz to 800 terahertz. I already have mentioned this. And primarily it uses LED lighting. Okay, and the prime reason to focus on visible light is because we want illumination to coexist with communication. So that's what I have said. It can provide both illumination and communication. And this is just a brief schematic of a VLC network. So you have LED bulbs which are emitting light. And one question that can come in someone's mind is, why are we using LEDs? Are there other sources which can emit visible light, or why are we focusing on LEDs as our transmitter for VLC network? And the reason is, if you look at this chart, this is a very important chart, has been taken from this reference paper. On this axis, we are focusing on luminous efficacy. Okay, most of these sources that we have, lightning sources, they operate on electricity. So the question that we have to ask, per watt of electric power that is given to these sources, how many lumens they can provide? Okay, so luminous efficacy is the measure of that ratio. How many lumens per watt? Okay, and intuitively you can all appreciate that higher is the luminous efficacy of a source, better is that source, right? That means it can provide more light for a given electrical power. So if we look at these LEDs, they have luminous efficacy of 300. That's very good, right? Compare this to fluorescent bulbs, which we used in the past. They have luminous efficacy of somewhere around 70. Okay, incandescent has even smaller luminous efficacy, and candles has even smaller luminous efficacy. Why are we talking about luminous efficacy for the candles? Because they do not require any electrical power. So you can imagine that in production of these candles also we would have used some power, right? So luminous efficacy is approximated for a candle. It's not really lumens per watt, but you can imagine this as how much energy you might have spent in getting this candle made. Okay, so one parameter that we would use for any source is what is its luminous efficacy, and clearly LEDs are the winner. The second, if we come to this axis, then we are looking at lifetime hours. That means how many hours a source can work without failing. And for LEDs, this is about 1 lakh hours. Okay, and this is also much larger than that is for fluorescent and for incandescent. Okay, so both in terms of, yes, there is a question.
Participants,
So,
please mute yourself, sir. You may continue. I think no question was there.
okay, so both in terms of luminous efficacy and lifetime hours, LED is clearly the winner. Also, this is reflected in this production of these sources. So if I look at this chart, so this brown color bars stands for how many units of LEDs would be manufactured. And from 2013 onwards, this brown colored graph is rising. Okay, that means industry also has felt that the LEDs will be becoming more and more popular. So it is more advantageous to manufacture these LEDs. Okay. So industries have also realized this, and now you have more LEDs produced compared to that was in the past. So industry is also agreeing, and scientifically also we know that LEDs have a higher luminous efficacy and higher lifetime hours, and so this is the way forward. So when we are talking about LEDs, there are different kinds of LEDs. One is this phosphor coated LEDs. Okay. Then you have red, green, blue LEDs. We have micro LEDs. We have organic LEDs. So if we look to this micro LEDs, this is usually used in biosensors because it has very small luminous efficacy. It doesn't even have any luminous efficacy. Okay. And organic LEDs are used for the display purposes. Again, this is because they have slightly lower luminous efficacy and their complexity is also very high, and their bandwidth is also very small. Okay, so when we are looking to use sources for communication, we are concentrating on two factors: communication and illumination. These are the two things. So we are focusing on the bandwidth. They should have good bandwidth and they should have good luminous efficacy. So clearly phosphor coated LEDs have good luminous efficacy and they have reasonably okay bandwidth. I wouldn't say this bandwidth is great, but this is kind of okay. Okay, so at IIT Delhi, we have been using phosphor coated LEDs for this purpose, right? Other alternatives could have been this red, green, blue LEDs because they have more bandwidth and they have okay luminous efficacy. But the problem with this red, green, blue LEDs, it's slightly more complicated to use them. Okay, so the choice that we have for communication is to use either phosphor coated LEDs or red, green, blue LEDs, and we are sticking with phosphor coated LED at IIT Delhi. Now, one point that I would like to mention, because we have mentioned that this phosphor coated LEDs have smaller bandwidth, is there a way to increase the bandwidth of these phosphorus coated LEDs? That's the question that we are asking. So let us try to understand how this PC LEDs work. So a blue light hits a phosphor that creates phosphorescence, which produces yellow light, and you also have this blue light that is incidenting on this phosphor. Result of yellow light and blue light is a white light. This is a very simplistic picture of what actually happens, right? So that everyone can follow this. So this is how we have this white light. Now this process of phosphorescence is a slow process. Okay, so the modulation bandwidth of these LEDs is limited because of this process of phosphorescence. Okay, so what we can do is we can use a blue filter which kills all this yellow light, and at the output of this receiver, if you keep a blue filter, you only have blue light. Okay, so then what can happen is the bandwidth of these sources can be increased. Okay, of course at the cost of reducing some signal power. That would happen if we use a filter, blue filter, because all the yellow light will go away. So signal power reaching the photodiode will reduce. But if we want to increase the bandwidth, this is one way by which you can do this. Put a blue filter, only allows blue light, kills all the yellow light, and increases the modulation bandwidth of the sources. This is one idea that we can use. Okay, so blue filter is what kills the slow phosphorescence and imparts higher bandwidth. And after blue filter, you can push this bandwidth from 3 megahertz to 4 megahertz to up to 100 megahertz. So a lot of increase in this bandwidth. So far we have been saying that we are focusing on visible light communication, which uses LED bulbs, and we know why LEDs now, because LEDs provides us high reliability and this has a good luminous efficacy, which means it has higher energy efficiency. And the way we see it, we would be using phosphor coated LEDs with blue filters. It looks like a good option, right? At least for hundreds of Mbps. Okay, so again, we will like to summarize and add few more motivations to this VLC network. So if someone asks you why VLC, then the first answer is because RF spectrum is regulated. Okay, you have to pay. So Wi-Fi currently uses 2.4 gigahertz, which is not a licensed band. So you can use Wi-Fi for free. If we look at the frequencies of the Wi-Fi that currently is installed in most houses and offices is free. But the newer versions of Wi-Fi, which may be using higher frequencies, right? These frequencies may be licensed, and so the cost of these networks might increase. Okay, so RF spectrum is anyway regulated, and we say that you have any operator who is using this RF spectrum may have to pay to the government. Second point is there is capacity crunch on these RF networks, right? So a lot of devices currently are using RF networks, and so these frequencies are overloaded, and thus we can use, if we can add a new network based on these light frequencies, then you can reduce some of that capacity crunch. It has low electromagnetic interference, VLC. So sometimes you might have noticed in your home, if you're using Wi-Fi network and if you turn on your microwave, the signal degrades, right? Because the radio frequencies have a very high electromagnetic interference. So it can be affected by microwave ovens. But that is not the case with VLC. It's very secure. Why is this secure? Because it uses light and light stays within a room. It cannot go out of the room, right? So there cannot be any chances of dropping and things like that. No one can hear to your signal because the signal remains confined in your room. And because the signal stays within a room, we can do spatial reusing. So in this room, you can use one light, right? In the other room, you can use the same light, and there is no collision. So this is known as spatial reusing. It's very safe. We have been exposed to lights for centuries. We didn't have any harmful effects of the lights so far. So light is a very safe thing to be used, and so VLC is much more safer than RF. It's very energy efficient, and it can integrate and coexist with existing lighting infrastructure, and so that is very good about this. So there are a lot of motivations to use visible light communication, and we hope that in few years from now at least this will become a reality. Applications of VLC. So VLC can be used for various purposes. The thing that we are focusing on in this lecture is indoor wireless communication, but it can be used in RF interference sensitive places, for example, in hospitals or in other places which are very sensitive to RF interference. You can use VLC, it's very secure. We can do some Wi-Fi data offloading. You can use this for energy harvesting, indoor positioning, alert system, underwater communication, error networking, and so on and so forth. So there are many applications of visible light communication. So by now, I think everyone must have understood what is Li-Fi and what is VLC. VLC is a part of Li-Fi, and everyone must have understood why are we focusing on this VLC. Is there a question from the audience so far? Okay, no questions. So then we will move to the second part of the lecture, and that is about VLC system model. We will be presenting the system model that is used in visible light communication. So this might become slightly technical for some of you. So I will like to slow down myself. So if we look at this chart, so you know that LED is a diode, right? So you have a certain current flowing in through this diode, and corresponding to this current, you have a power. Okay. And this power versus current, or luminous efficacy versus current, or intensity versus current, you can use anything on this y-axis. is almost linear with respect to current. Okay, so LED is almost a linear source, right? So that is a good thing. So we can say the power that is emitted out of this LEDs is proportional to this current IT. And this IT, the current signal, can have the information. So this IT can be of this form. So this is the signal that people used in communication systems. If you have done any course in communication system, you know that your message signal is something like this. What are these? These are the numbers that you want to transmit. SKs are some numbers, 2, 3, 5, 10, 100, whatever. And these numbers are modulating the amplitude of these pulses. Okay. So for example, just to make this little bit clearer, I will write something if it helps. So suppose you have this signal. So this is my PT. Okay. And then this pulse remains confined, let's say for a certain time duration. Normally this is denoted by capital T. Then after this capital T time interval, you can have another pulse. Then this pulse is PT minus T. Okay. And this minus is also coming in here. Then you can have, let's say, another pulse. You can have another pulse, right? So this pulse is PT minus 2T. And this pulse is PT minus 3T. So if I am transmitting this waveform, I can write this waveform as PT minus PT minus T plus PT minus 2T plus PT minus 3T, right? So this is the waveform. If I want to transmit this waveform, this will be the corresponding signal. And this thing I can represent this simply by using this equation. So SKs are the amplitudes of these pulses. So here the amplitude is 1, minus 1, 1, and 1. So SKs are the amplitudes of these pulses. And this denotes that you have pulse and the shifted versions of these pulses. Okay. So the information signal in digital communication is mostly like this. And this can be the form of the current that you may feed to the LEDs. And the power that LED will transmit would be proportional to this current. I hope this is clear. So the thing in for a diode is this IT has to be strictly greater than 0. That is the first restriction, right? If you have IT negative, then of course this will not be passed by the LEDs, right? So for PT being proportional to IT, there has to be one condition on IT. IT has to be strictly positive, okay, for all time intervals. Then one thing we have to understand, LED is not an oscillator. So what is an oscillator? So in communication systems, you may have seen, for example, amplitude modulation. You might have seen MT, which is the message signal. It can be easily multiplied with an cos omega naught t kind of waveform, or maybe sin omega naught t. Okay, so how is this cos omega naught t is produced, or how is this sin omega naught t is produced? This is produced by an oscillator. So an oscillator, what I mean with an oscillator, it's a sinusoidal source, something which produces cos omega naught t or sin omega naught t. If something produces, if I have a box, and if this box produces cos omega naught t, okay, we know then we say this as an oscillator. Then the next question is, it's a coherent source. right? Why is this a coherent source? Because at all time instances, you know the phase of the output of this source. So if someone asks me, what is the phase at t equals to 1 second? I know the phase is omega naught. If someone asks me what is the phase at t equals to 2 seconds, I can say the phase is 2 omega naught, and so on and so forth. So at each time instance, I can tell you the phase of the waveform that the source is producing. So this kind of source is known as a coherent source. Okay. So LED is not a coherent source. First important property of what is an LED. It's a non-coherent source. That means it cannot produce these sinusoidal waveforms at its output. Okay, again a very simplistic picture. So if you have certain message, you cannot use LEDs to multiply this kind of thing to this message. That's not possible. That's one thing that we have to understand. That means now we are slightly jumping into more and more complications. But I guess if you just concentrate for a few minutes, then this would be addressed. When I'm saying LED is not an oscillator or it is a non-coherent source, what I mean with this? It means that the electric field produced by the LEDs cannot be complex. So let us look at, suppose electric field that we have out of a source. Let us imagine this to be complex. So it is something like this. Okay. Now what I understand by this complex electric field, or what I understand with this complex numbers. In physical world, there is nothing complex, right? Everything is real. Okay. So what I understand by the field being complex, the field can never be complex. It has to be always real, whether it's a coherent source or a non-coherent source or whatever may be the source. So this complex things have been introduced in this literature to simplify maths. That's it. It has no physical relevance. So when I'm saying the field is complex, the physical reality is, what is the physical reality? That means ET can be something like this. ERT cos omega naught t minus EIT sin omega naught t. If the electric field is something like this, is this a complex quantity? No, it's a completely real quantity. So instead of talking about this electric field, I can represent this electric field like this because it's mathematically easier to deal with this quantity rather than this quantity. Just for mathematical ease, we convert this quantity into this quantity and we say that the electric field is complex. But the physical meaning of this thing is that the electric field is something like this. Okay. And why we are converting this thing into this thing? Because cos omega naught t is orthogonal to sin omega naught t. This you might have studied in signals and systems or in some other courses. So if cos omega naught t is orthogonal to sin omega naught t, what we can do is you can separate out ERT and EIT, right? If someone gives you this electric field represented by this equation, the question that you need to ask yourself is, can I separate out its ERT and EIT? The answer is yes. Similarly, if someone gives you a complex number, it's easy to separate out the real part and imaginary part, right? So real part sits here, imaginary part sits here. That means you can separate out the two parts quite easily. Okay. Similarly, if someone gives you this, then you can separate it out. So these two things are essentially the same thing. So again, I am repeating, if we have electric field like this, mathematically we can represent it like this. So this is the meaning of electric field being complex. For LEDs, because it's not an oscillator, you cannot have this. You cannot have cos omega naught t. You cannot have sin omega naught t. Okay, so understand. So the electric field of the LEDs, mathematically, you cannot assume it to be complex. That means what? That means the complex modulation schemes are not possible. Complex modulation schemes like quadrature amplitude modulation, of phase shift keying. These are not possible. So in phase shift keying, if you remember the constellation, it's something like this. You have some points, right? And it uses two-dimensional things, right? Something here, something here. So PSK, quadrature amplitude modulations, all these things are examples of complex modulations. So over LEDs, you cannot do complex modulations. You cannot do quadrature amplitude modulation. You cannot do phase shift keying. Only simple optical modulation schemes like intensity modulation or on-off keying or pulse position modulation can be used because they are one-dimensional quantities. They do not involve multiple dimensions in this sense. Okay, so over LEDs, we can simply do this intensity modulation. And this is what is happening. The power of this LED is directly proportional to the current. And in current, you have information. That means by information, you can change the power of the LEDs. Okay. So that's fine. Now this, we have understood this clearly. I guess there is no confusion over this part. And the third point is the IT, the current that you feed to this LED. So if this is my LED, if I ask you a question, can this current that you feed to this LED, can this current be complex? And the answer is yes, because what I mean by complex current simply means something like this, right? So as long as IT is all positive, okay, if IT is all positive, you can definitely feed this current to this LED and the output of this LED will be proportional to the current input. So that is possible. So that's why you hear that over this visible light communication I am doing OFDM. OFDM is a complex modulation scheme, but we have to differentiate between the two things. The current can be complex, no problem with that. And the power that is produced out of this LEDs will be proportional to the current. Okay, so here we have only intensity modulation, the way power is mapped to the current, but the current can be complex. There's no problem with that as long as the current is all positive. Is there any doubt? This is slightly complicated, so I will like to pause and wait for maybe one or two questions if there is any. Okay, good. So let's move ahead. And things can go on becoming more complicated. So we have seen that PT is proportional to the current. That's fine. Then VLC is a wireless channel. You have to transmit a signal in the air, and any wireless channel is a time varying channel. Any wireless channel is a linear. I will not go into the details of that. As a linear and time varying. Okay. So in signals and systems, you must have studied about LTI, linear time invariant channels. So it's not linear time invariant, it's linear time varying. And linear time varying systems can be characterized using impulse response, which is a two-dimensional thing. Okay, so LTI systems, the impulse response looks like this, h of t. Okay, what is the meaning of this? So if you have an impulse applied to an LTI system, you get some response. Okay, and this response does not depend upon when the impulse is applied. So this response is a one-dimensional quantity. But for a time varying channel, the impulse response also depends upon when the impulse is applied. So the impulse response for a wireless channel looks like this. And we can use the convolution same as before. So you can convolve this PT with this impulse response and you can find out this output. Okay, so this is the output of a wireless channel. This thing goes to a photodiode or a photodetector, and the photodetector converts this electric field to the current by using this relationship. So whatever is YT, it multiplies this with this R, which is known as the responsivity of the photodiode. And after this photodiode, you get the current. Okay, so the current at the photodiode is again this quantity. Okay, so I know that PT is something like this. So I can expand this up in this form. And then what I can do is I can use a little bit more maths. So let me try to explain, because sometimes this can be confusing. So I will like to explain this up. So YT we know is this thing. So if I want to write this in some other form, how can I write this? So look at this equation. PT is, let's say, is the inverse Fourier transform of this. Okay, so this PT, this is the inverse Fourier transform of this quantity. Similarly, we can write h lambda t as this. And what I understand with this is, if I provide this system an impulse, which is weighted by this PF, then the output of this system, similarly as you have done in for linear time invariant systems, then the output is this factor multiplied by this signal. Okay, so just as you have done in linear time invariant system, if we have an LTI system, if a complex exponential e to the power j2 pi ft is input to this LTI system, what is the output? Output is hf times e to the power j2 pi ft. Everyone knows this. Okay, this is the property of an LTI system. This signal is an eigenfunction of an LTI system. That means its output is this function multiplied by certain constant, and this constant is h of f, or frequency response. This is constant with respect to time. Okay, so you get this thing out. Similarly here, everything remains exactly same. If we give this as an input to my system, okay, then for every this quantity, so if I just give this, let's say, as an input, my output is hft multiplied by this quantity. So this input, this PT, will lead to this output. Everything remains almost same here. So, or an easy way to understand what would be the output in terms of frequency responses. So we know that based on just what I have explained, IPT is also this signal. And if we assume flat and slow fading, what I mean by flat and slow fading? Flat fading means for the input bandwidth, suppose my signal bandwidth is like this. Suppose this is the spectrum of my signal. The spectrum of channel is broader, and this remains constant for the input frequencies. Okay, so that is the meaning of flat fading. Slow fading means this frequency response also does not vary very suddenly, it varies very slowly. Okay, so if the signal is for a certain time duration, let's say 1 nanosecond, if I am feeding one signal or pulse of 1 nanosecond, then my channel will remain constant up to 1 milliseconds. So that is the meaning of the slow fading. So if I assume flat and slow fading, under that assumption, I can carry out this expression. And finally, just some mathematics. I will not go into the details of each and every steps. Some simple steps you can think yourself. We get a signal like this. The important point to see, and that is the most important point, is the current that is coming out of the photodiode after we have used this mesh filter and other things is proportional to SK. SK contains the information, right? SK is what has the information. The digital information that you want to transmit is where? Is this? It is this in SK. So if we use this mesh filter, if we use this wireless channel, and if we use some mathematics, then what we can see after all of it, that the current that is coming out of your mesh filter after the photodiode has this SK inbuilt. Okay, so that means the communication is possible in the VLC. Bit of maths, but I think it's fine. Now let us compare. So far we have seen the LED characteristics. What can we do over these LEDs? How does the system model of this VLC looks like? Now it is the time to contrast this with radio signals. So bandwidth is regulated of radios, yes. For IMDD, IMDD stands for intensity modulation and direct detection. That is the system for VLC. The bandwidth is not regulated. Radio signal can pass through walls. IMDD signal cannot pass through walls. Radio signal goes through this multipath fading. Yes. IMDD multipath fading doesn't happen. Why it doesn't happen? Because the receiver size or the receiver aperture is much larger than the wavelength of the light. Okay, so if I'm having a large receiver, this point you can have constructive interference. This point you can have destructive interference. This point constructive, this point destructive, constructive, destructive, and so on and so forth. Receiver aperture is much larger than the wavelength of the light. So within one receiver, you can have a lot of constructive and destructive interferences. And on an average, everything evens out. So there's no multipath fading in IMDD links, but you can have multipath distortion. Multipath fading is different from multipath distortion. Multipath distortion happens because of the delay spread. If you have a pulse like this, and the same pulse gets reflected and reaches with certain delay, then overall the pulse signal will look like this. So there may be pulse parotony. So multipath distortion happens. The path loss in both these systems is high. Most dominant noise in IMDD systems is background light. Input XT represents amplitude in radio systems. In IMDD systems, it's power. That's what we have said, right? Signal to noise ratio is this quantity in both these systems. And because input XT represent power, that this thing requires higher transmitted power. And in IMDD systems, we want waveform with high peak to average ratio. That was not the case in radio systems. So there are some differences between radio systems and IMDD systems, and the most important difference happens because of the fact that the signal that we are transmitting in radio systems is the amplitude, whereas the signal that we are transmitting in IMDD systems is power. So some differences are with respect to the transmitted power requirements and the peak to average ratio of the waveforms. So again, the picture of visible light networks. So we have LED lamp, we have photodetector, and we have other components. which is like in any communication system. So I will skip this slide because I'm running out of time. So let us focus on channel modeling. It's important to understand, if you have done any course in wireless communication, the most important thing to ask is, what is the channel characteristics? How does the channel looks like? What is the delay spread of the channel? What is the intersymbol interference possibilities in a channel? What data rate you can transmit over a channel? So these are important questions, and for to answer these questions, we have done some channel modeling and we have got some results. So again, I will not go into the details of these slides. I will just present the main results. I will skip these slides. So these are the main results. The research has happened at IIT Delhi. So as I have mentioned, the first important point that we have to worry about is the delay spread. What is the delay spread of a VLC channel? And this delay spread depends upon how many reflections you want to consider in your simulations. Okay. For example, if the LED is transmitting some light, this may get reflected here, 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 and so on and so forth. So how many reflections do we have to consider? That's the first question. And what is the reflectivity at the surfaces that you have assumed? So if we assume reflectivity as 0.2, then we get these bunch of results. And if we consider the reflectivity of 0.8, which is really high, we get these sort of results. That means delay spread is a function of reflectivity. If you have more reflective surfaces, then the delay spread is higher. If we have less reflective surfaces, then the delay spread is smaller. That's point number one. Second thing is, if you see, then these results do not depend upon or do not significantly depend upon the number of reflections. Okay, that means if we can consider up to 3 reflections, that's more or less okay. You do not have to consider 100 reflections, because if you want to do that, then your simulation time will go out. It will become very large. Okay, so up to 3 reflections is what you want to have. So that's the message. And the delay spread, the maximum value is what should concern is around 0.05 nanoseconds. 0.005 nanoseconds. That's very small. So from delay spread, we can go to this coherence bandwidth. And if we look at the coherence bandwidth, the minimum coherence bandwidth that we have is 30 gigahertz. That's good enough bandwidth if you want to transmit 100 Mbps. So the message from this study is that if you are using phosphor coated LEDs, then the channel is not going to trouble you. If you want to transmit 100 Mbps, maybe even 1 Gbps, it should be okay, because the coherence bandwidth of the channel is very large, 30 gigahertz. Okay, so the channel itself is not problematic. That is the outcome of this research. So we are not using any fancy modulation schemes. Fancy modulation schemes means the modulation schemes which can get you higher spectral efficiency. We are not doing that. Okay, fine. So we are restricting ourselves to simple modulation schemes like on-off keying, and maybe to 4-com, nothing more than that. So BR also depends upon the channel. So this is what we see, and yeah, I haven't mentioned here, this delay spread depends upon the LED semi-angle. What is the LED semi-angle? So if you have an LED, the cone in which an LED transmits most of its light is characterized by its semi-angle. So all these parameters clearly depends upon what is the LED semi-angle, and you can always design the system with the correct LED semi-angle. So we see that LED semi-angle somewhere between 10 to 15 degree is best. So our VLC systems must use it. Okay. Similarly, the BR also depends upon the LED semi-angles, and you can do the characterization. I will skip this slide, so not too important. Then the modulation schemes that we want to use in VLC, it should have flickering, mitigation, and it can have dimming support. So this is, you can see what is flickering. Okay, so flickering is very irritating. Even if you see the slide for a while, you would not like to see it again. It creates headaches, nausea, and so on and so forth. And it should be doing dimming support. Dimming is you should be able to tailor the power of this source. So you might want to receive your internet even while sleeping. Okay, you do not want to miss a WhatsApp call. So the communication system must work with a very low power also. Okay, and the communication source must not flicker. These are the two things. So flickering we can avoid by using what is known as run length coding, and it's not very difficult thing to do. So I will not talk about this. Dimming is interesting because we have to change the modulation schemes. So one example by which we can increase the dimming support is by using variable on-off keying. So I will just explain this variable on-off keying. So what happens in simple on-off keying, bit 1 you transmit all the time, and bit 0 you transmit for no time. So an average is almost at the 50%. But here what we do for bit 1, this is my signal. The green one is the signal, and this is the filler data. So it does not contain any information, but we transmit this. And bit 0 also has this filler data. So you can see that now the average has increased more than 50%, and this is the way by which we can increase the dimming support. Contrast this to this case where for bit 1 you do not have anything, and bit 0 you do not have anything. So the average of these two quantities is less than 50%. So we can make the average more than 50% or less than 50% by having either the filler data or by having no data at all, even for the bit 1 for a certain time period. And this is what happens in variable on-off key. So these are the schemes. You can have variable pulse position modulation also on the similar lines. So we have done some power spectral analysis of these sources, and not so important as we have. So if you look at these figures, you can estimate how much bandwidth would be required by these sources. And this is the BR study of these sources. So we have done two kinds of analysis, one by having ZFE, zero forcing equalization, and by having no zero forcing equalization. So the bottom line is that you can have dimming enabled modulation schemes, which will change your BR and so on and so forth. And you can reduce some of this BR by having zero forcing equalization at your receiver. Next, we move to the multiplexing techniques which are used in visible light communication, and the multiplexing techniques that we are focusing on is non-orthogonal multiple access. And this is becoming a very powerful multiplexing techniques even for the other wireless communication systems. I would take a break of 1 minute, and I would just also invite you to ask questions if you have any. Okay, so let us start this. What is the idea behind non-orthogonal multiple access? Again, you could have used other modulation, other multiplexing techniques as well, for example, OFDM. Okay, but NOMA has shown that you can get a better spectral efficiency with NOMA than with OFDM. Okay, so what is the idea of NOMA? I would try to illustrate this idea of NOMA by equation. So for example, if two sources are transmitting, there's a transmitter 1 and there's a transmitter 2. Transmitter 1 transmits amplitude 10 or 0, and transmitter 2 transmits amplitude 1 or 0. Okay, we can choose to vary the amplitudes transmitted by these two transmitters. And there is one receiver which receives the signal from both these transmitter 1 and transmitter 2. Suppose receiver receives 0 and there is no noise. Okay, receiver receives 0. When the receiver receives 0, it can immediately deduce that transmitter 1 may have transmitted 0 and transmitter 2 also may have transmitted 0. So let me make kind of a truth table. If transmitter 1 transmits 0, transmitter 2 transmits 0, receiver receives 0. If this transmits 0 and this transmits 1, receiver receives 1. If the transmitter 1 transmits 1 and this transmits 0, it receives 10. If this transmits 1 and this transmitted 1, then the receiver receives 11. So receiver, it receives these 4 amplitude levels. Again, this is in the absence of noise. And by looking at these amplitude levels, can the receiver deduce what transmitter 1 and transmitter 2 has transmitted? Yes, of course. And this is known as power domain multiplexing. We are changing the amplitudes at the transmitter significantly. And so when the receiver receives a signal, based on the received signal, it can deduce what these transmitters might have transmitted. Contrast this with the case when the transmitter 1 and transmitter 2 transmits the same amplitude, 1 or 0. Now let us make a truth table for that. It transmits 0, it transmits 0, receiver receives 0. It transmits 0, it transmits 1, it receives 1. This 1, this 0, it receives 1. This 1, it receives 2. Now receiver receives 1. And when it receives 1, it has no way to decide whether transmitter 1 has transmitted or transmitter 2 has transmitted. So if both these transmitters are using the same amplitudes, then what would happen? And if they transmit at the same time also, then the collision will happen. Then collision means the receiver, by receiving something, it would have no idea who has transmitted what. This is known as collision. So collision will happen. However, if you change the amplitudes transmitted by these transmitters, then by looking at the amplitudes of the received signal, you would know who has transmitted what, and you can separate out, you can deduce from the received signal the signals of each individual user. So in VLC, we use power domain NOMA. Different users transmit different amounts of power. And what is the way to deduce who has transmitted what? You can use successive interference cancellation. And what is the idea behind successive interference cancellation? We can, for example, if let us assume I am receiving a certain signal Y This is what I receive. And by looking at the Y, I have to make a decision. Let us say I go with the user 2 first. So this user, this transmitter, I'm trying to decide. And I have decided what it has transmitted. Okay. So let us say we have decided that it has transmitted 1 after looking at Y. So you would subtract out 1 and you will look at this signal Y minus 1 and then you will decide what transmitter 1 has transmitted. Okay, so this is the idea behind successive interference cancellation. You look at the received quantity and by looking at the received quantity, you find out what one user has transmitted. Once you have taken that decision, you subtract out that quantity from the received signal and you look at what user 2 has transmitted, and so on and so forth. You carry out this process and you deduce what all users may have transmitted. And this process is known as successive interference cancellation. So now we are proposing a power allocation scheme for NOMA, and this we have done. And intuitively what we are saying, suppose I have one transmitter and there are 3 users. Okay, so this user is the closest, so it will have the highest channel coefficient H1. This will have second highest and this is the farthest, so it will have the channel coefficient H3 such that H1 is larger than H2 is larger than H3. So what we are saying, you have to transmit the power to these 3 users in such a way that the received power at these 3 users is same. Okay. So for example, if my H3 is the smallest, I would transmit. So in transmitter 1, let's say I am transmitting 3 powers, P1, P2 and P3. If H3 is smallest, then P3 has to be the largest. P2 has to be smaller than P3 but larger than P1 and so on. So this scheme will ensure that all users roughly get the same power and they have the same BR performance. So for this we have found out the power allocation factor. That means if we have these 3 users like this, then we know that P1 should be smaller than P2, should be smaller than P3. But what is the ratio of P3 by P2? This ratio is given by power allocation factor. This has to be larger than 1. So P3 by P2 should be gamma, and this gamma is the power allocation factor. With what factors, with what ratios these powers vary, and we have computed this. It's a little bit slightly complicated, and this is the formula that we can use, and this will ensure that all users will have the same BR performance. And we have compared with the existing power allocation schemes, GRP and NGTPA, and we can see that our proposed power allocation scheme is much better both in BR fairness and throughput fairness than the other 2 schemes. Finally, the time for some demos. This is what we have demonstrated in IMC 2019. So we have a transmitted video here and the received video. As we block, the received video stops. So we have demonstrated the video communication using Li-Fi link. So it's possible. I haven't included the latest demo, but it is put up in my website. So if you can look at my website, you have the latest demo of this Li-Fi link, where we have scaled the bit rates to about 40 Mbps. So in 2019, this was only 4 Mbps. Now we have made this to 20 Mbps. The same system, the same thing, but with a better bit rate. Yes, 20 Mbps. And this is 20 Mbps. So maybe if I can show you that video, just give me a second, because it's slightly different. In this video. Can you see this YouTube video? So here what we have, we are showing is one Wi-Fi transmitter and two receivers. Okay. And we can, over this Wi-Fi setup, we are transmitting two video streams simultaneously. So we are using time division multiple access, and both receivers receives different videos. Okay. So in this setup, we have also incorporated time division multiplexing, which is what is used in any practical networks. And the data rate is even higher. So this Wi-Fi transmitter can transmit up to 40 Mbps. And these receivers can also move. Okay, so first we show the effect of shadowing. When we shadow this video stop. And if we block this video will stop. And we also show the effect of moving these receivers. So you can move one receiver, and even then the video continues to stream. Okay, so if you are interested, you can look at this demo yourself, and we have other demos also uploaded. So this is in the developmental stage. We have developed this using FPGAs. So these are the two FPGA boards which we have used, and we are streaming the videos from the transmitter to receiver, just showing you the quality of the videos that we have. You can again look at this video much more detail later on. And this is about lens system that we have developed for Wi-Fi link. So the lens should orient itself to the light, right? To focus the light to the photodiode. So as you can see that as we are changing the light source, which is coming from the phone, the receiver is orienting itself. Okay. So the Wi-Fi has the latest standard, which is ITU G.991, which is for high-speed indoor visible light communication transceiver, a system architecture, physical layer, and data link layer specification. You can read this latest reference for more information on Wi-Fi. So this concludes my talk. If you have any questions, I will be happy to answer it. Thank you so much for your time and attention.
Thank you, sir, for the wonderful talk. So now it's over to participants. If you have any queries, please come up with your questions.
I'm not able to hear you.
Sir, can you hear me now? Hello.
Just okay, I have.
Hello, sir, can you hear me now? Nathani, sir, am I audible?
Yes, you are.
Yeah, you are audible to me now. Sorry.
Okay. Sir, I was asking the participants to come up with their queries.
Okay.
And thank you for the wonderful session, sir.
Thank you so much. Thank you so much.
Yes, participants.
Hello.
Please.
Hello.
Yes,
Sir,
please
am I
continue.
audible?
Yes, you are
Yeah,
audible.
you are
Please.
audible.
Sir, my as Professor Dixit, he considered that on-off keying modulation will be the basic technique would be using for modulation scheme. My question is, what will be the drawback or what will be the bottleneck when we will be using this phase modulation or phase and amplitude modulation together?
See, I
Is it
have
possible?
no, I have already discussed in my slides that there are two kinds of modulation schemes in Li-Fi. One is the subcarrier modulation, which is how are you changing the digital information in RF domain. Okay. And then the second is optical modulation. So there are two sorts of modulation schemes that we can use over Li-Fi. One is subcarrier modulation and one is the optical modulation. So when we are talking about
Sir,
optical modulation, sorry,
okay.
when we are talking
Sir,
about optical,
actually, sir, we can go for phase modulation in optical domain also. As I'm a
no,
PhD scholar in IIT Kanpur actually.
no,
So
no.
I'm
Phase,
using the phase modulation.
yeah. So phase modulation we cannot use over LEDs. You can use phase modulation over lasers. Okay. So
Yes,
laser is a coherent source. So if we want to use laser,
yes,
you can do phase modulation. But for visible light
okay.
communication, we are using LEDs as the sources. So over LEDs, we cannot use phase modulation. LEDs is restricted. We are restricted to use intensity
Only for
modulation.
intensity modulation.
Yeah.
Okay,
Okay. So, but yeah, in subcarrier, you can use anything. That's fine.
okay. Okay. Thank you, sir.
Thank you, Nidhi.
Yes, any other participant wants to ask anything from sir? Participants, any questions? Sir, I guess there are no further questions.
Hello.
Okay, there is some.
Hello.
Yes, please ask.
Yes. Maybe there are some network issues.
Yes, sir, I think connectivity was lost. Okay, I think there are no more questions, sir. If you would allow, then participants can contact you by email.
Yeah, definitely. If you have other questions, you can write me an email if you're interested to learn more about it. We will provide you necessary information for that. So anyone who is interested to contact me is more than welcome. If you want to think about this topic and ask me a question later on, that's also fine.
All right, sir. Then I guess we can conclude the session. Sir, thank you for joining with us and sparing your time, your valuable time.
Thank
You,
you,
sir.
Sanjeev. Thank you, Sanjeev,
Thank you,
for your
Abhishek.
time. Thank you. Thank you.
Thank you very much. I used to disturb you time to time, right? Thank you very much.
Thank you. Bye.
Bye.
Yes.
Okay, thank you, Sandeep. Huh?
Thank you, sir. Thank you.
Okay, so
Okay,
see you.
participants will, yes, participants will meet for the next session.